All right, I think we're live. It's so much simpler when I just have to point the camera at myself and not have all the other people all at the same time. So, as always, if you're listening to this as a podcast, which is smart, because then you can listen to it at your own leisure, then apologize for the weird beginnings these always have. But hey, everybody, we're back from hiatus. It's been 2 months since we've been doing any of these live streams, and I missed you all. I really do. I actually really enjoy doing these live streams, and it's for the first couple of weeks, it's like this. I don't know. There's like this muscle that you're just like, every week on schedule, you're doing these various projects, and then suddenly you're just sort of cut loose, and you have no agenda and no schedule, and it's nice to be able to have the time to sort of, I don't know, not have to find internet, but at the same time, I really do miss this time we have together every week. So we're back. And this is, of course, just the way to be completely interactive, to give you 100% of my focused attention, where we can answer all of your questions about space and astronomy, dig down into every rabbit hole you guys want to go down to completely, unscripted, unplanned, wherever it goes. New season. Right now, it's just you and me right now, but I think we're going to definitely try to bring on some more guests. I've got a bunch of really interesting people that I've been reaching out to, talking to. Some people, some names some names you might not know. And but I'm always open to anyone who you want me to interview here on Open Space. Really kind of dig into it. And at the same time, I know that people do like to have some of just the pure QA time as well, so that you can digest all of the space material that we've been throwing at you for the last for the last week. As you've noticed, we have definitely increased the volume of videos that have been coming out of the channel. We've kind of had two things that Chad and I have really been trying to do. One is try to stick to a schedule. And that it's been mostly okay, although every now and then, we'll start working on a website and realize it's a can of worms that we've opened up, and we have trouble sort of putting the whole thing together, so it slips a bit. But I think we've been pretty good about releasing them pretty much within a couple of minutes of when they're supposed to, both early to the patrons as well as on time to the public. And we've doubled up, so 2 episodes a week, and they're also getting longer. The one we did about L2 and L3 was 17 minutes long, I think. Yeah, it was tough. But Chad is a machine. He's been able to stay on top of this, edit like crazy. And I've got no shortage of topics. It's funny, the more videos we produce, the longer my list of topics gets. Like literally right now, you should see my list of ideas. It's probably about 100 ideas right now. And many of them are sort of partially fleshed out. So I've got a bunch of sources, a bunch of like articles that I want to, journal articles and stuff that I want to incorporate. So, I hope everyone's really enjoying that. Easy Tiger asks, where does the phrase can of worms come from? I have no idea. I'm assuming there's some place where worms come in cans, and then you open them up and you get more worms than you accounted for, more worms than you were hoping. You get a lot of worms. So I don't know. Where do words come from? Phrases. All right, let's get cracking. Kevin says, mixing concrete on the International Space Station, wouldn't we be using concrete on a moon, asteroid, or planet? So this is probably in relation to the story that went out today about the fact that the astronauts on board the International Space Station have been mixing concrete. And they've been doing this in, of course, the microgravity environment of the space station. Why would you do that, right? Well, the question is, like, what is going to be the best building structure to make things out of in space? When you can 3D print your stuff in space, why it doesn't need to be super lightweight. It doesn't need to come from the earth. It doesn't need to be folding or any of that. It just needs to, just be able to be formed in space. And, when you're looking at things like, say, radiation shielding, building up concrete as a shield, concrete blocks made from crushed up lunar regolith, is actually one of the ideas for how you would shield some space-based colony, some big rotating colony. You would just use raw concrete and you would just surround your space station with concrete. And so the question then is, if you're going to try and make this stuff in space, how does it work? Right? Does it set in the right way? Does it dry in the right way? Does it, how is it different? Is it as strong? If it's not as strong, how differently is it strong? I mean, these are all just questions. I mean, for this exact thing that we're talking about, right? Concrete in space. You could ask the same question about 10,000 other things that we do every day, right? How will using a computer work in space? How does lighting work in space? How does plumbing work in space? How does heating work in space? How does air conditioning? All this stuff. How do plants grow in space? In microgravity, in lower amounts of gravity, and you've got to test out every single possible option. And the reason that you want to do concrete is because, building materials in space, you're going to want to get them from space. You're going to want to take your material from an asteroid. You're going to want to take your material from the surface of the moon. You're going to launch it off into space, and then you're going to build with that. You want to avoid at all costs bringing things from the surface of the earth, because it's so ridiculously expensive to launch things off of Earth. And I don't think people really appreciate, I mean, obviously I've got my poster there. I don't think people really appreciate how awful and how much more expensive. I mean, to take something from the Earth to the moon, you're looking at $2,500 to $10,000 per kilogram right now. You have to multiply that by a factor of 10 or even a factor of 50 to carry that stuff up to the surface of the moon. And obviously, you're going to want to extract that stuff from the moon. So as much as we can produce in space, we're going to try to. And so concrete is just one thing. So an Easy Tiger says, could you make shotcrete from regolith? Yeah, there's been a bunch of really interesting technologies. We covered it a bit. We did an episode about in situ resource ISRU utilization. And one of these ideas is taking, scooping up regolith from the moon or Mars and then turning it into a kind of concrete. And there's a few additional things that you need to have. You need to have you may need something like magnesium to be able to do certain kinds of structures. But it's kind of amazing, actually, how well lunar regolith will turn into concrete. And if you've read Andy Weir's Moon Artemis book, he talks about how they just build everything out of aluminum on the moon, that if you go and you process the aluminum on the moon using heat and electricity, you get just ingots of aluminum out of just the regolith, and then you get oxygen as a byproduct, which of course you can use that for all kinds of things. Mix that with some hydrogen and you've got rocket fuel, you got water, you can breathe. So we need to learn all of these things. It's funny, right? Like going to the moon or going just out into space, we still have the same basic needs. We need to breathe, we need to eat, we need to be the right warmth. We need to have we need to have the right amount of air pressure. We need water. But how we'll get these things and what's the most efficient way to do it, that's where you kind of have to think completely out of the box and not have any real preconceived notions about how any of that stuff is going to work. You just have to test it. You just have to try different ideas. And eventually, after dozens, hundreds of years, people will figure out the solutions to all of these problems. All right, next question. Hallucination 8. Why do some planets spin in the opposite direction from others, or is this a myth? I know, probably a pretty basic question. No, so that's not a myth. There are two places in the solar system that are spinning in the kind of weird opposite direction. The first of these is Venus. So if you look at the orbit of Venus, it is turning very slowly backwards compared to all of the other planets in the solar system. And so the question is why, right? Why does Mercury, Earth, Jupiter, Saturn, Neptune, why do they all turn the same way, and yet Venus is going apparently backwards? And so there's two kind of thoughts about this. One is that something really big smashed into Venus a long time and just rolled it over. And then the other thing is that there was some kind of process of planetary migration. So early on in the history of the solar system, you've got this big cloud of gas and dust, and you've got these planets forming like nuggets inside this cloud of gas and dust. And as the planets are pulling in gas and dust, they're moving inward and outward, depending on sort of where the material is. And so they're kind of interacting with each other and influencing each other with their gravity. It could be that two planets came really close to each other, or they started out close to each other and flipped over Venus in the past. And the same thing with Uranus. You've got people have seen that, you could do it with a bunch of collisions to roll Uranus over onto its side. Like if you actually look at Uranus, its pole is pointed sideways, and it's almost like it's rolling sideways as it goes around the sun. And again, so it could have been the migration, like Neptune, which is farther out from the sun than Uranus is actually a little bigger than Uranus. And so you would actually think it would be, Jupiter the biggest, then Saturn, then Neptune, then Uranus. But at some point in the ancient past of the solar system, Uranus and Neptune switched places as part of this planetary migration. And that might have rolled Uranus over, although why Neptune wasn't rolled over. So it's a question. I mean, the best astronomers in the world don't have an answer to this yet. So, don't feel like you're confused. Rob Collins says, Fraser, what's your take on the Titan Lakes formation? So for people who missed this, a big news story broke today, came from NASA and a bunch of other places, that they think they understand these weird lakes that are on Titan, Saturn's largest moon. And so these are, of course, these lakes. They find them in the poles. They're filled with liquid methane. And one of the things that's really weird about them is they have this really big crater rim. And so any of the methods to form on Titan don't seem to explain why you would get this really big rim around the edge of the lake. And so the idea that's been proposed, and I had never heard this before today, so I'm sort of still kind of thinking about it, and it's like, do I do a video on this? I don't know yet, because there's a bunch of really interesting Titan research. So the idea is that there are these vast pockets of nitrogen gas underneath the surface of the world, and they have, for some reason, sort of exploded. These chambers of gas have exploded underneath the surface of the lake and blasted out like a pimple, like a volcano. And then the crater that remains got filled in with the constant methane rain that's falling. We need to go there, and we need to look close, and we need to follow this line of reasoning. It's a great idea. And again, one that I had never heard before. And when I hear about it, I love it. Adult film star. Why don't millionaires and billionaires go to the moon? Why don't millionaires and billionaires live on Antarctica, right? Antarctica is cold and desolate and far away, and a pretty terrible place to live, because it's a terrible place to live, right? And the moon is even worse. The moon is like, it's colder, except when it's hotter. There's no air to breathe. You've got to pay through the nose for every single thing that you want to bring from Earth, every possible good that you would need. So I can't imagine really, like, no, the millionaires and the billionaires are going to make their money in space. They're going to be mining asteroids. They're going to be making money by power generation, and who knows what they're going to do. But they're going to want to live down here on Earth, right? Earth is the best place in the universe that we know of. Although now there's some research that maybe you can have planets that have higher biodiversity than Earth. So I have to stop saying that, because now it looks like there might be planets better than Earth. But still, so no, I can't imagine anybody is going to want to actually leave Earth. And now Elon Musk, of course, that's the reason why he started SpaceX. He wants to leave Earth and start up a colony on Mars. And his rationale for that is that humanity needs a backup plan from all the various existential threats that we face. And I think, I did an open space last season where I talked to Phil Torres, and we talked about this idea that there is no escape from the existential threat. That if you go to the moon and you go to the Mars and you go live in the asteroid belt and you become a belter, any of that, there are just new and more elaborate ways to end all life. That now people have the ability to drop asteroids on each other. So there's no place to escape the existential threats. If the AI uprising happens here on Earth, well, the AI is just going to fly to space and chase you down and turn you into paper clips. So there really is there's no solution to the existential threats that humanity faces by going to space. We will take those existential threats with us. So, will that occur to Elon Musk? I don't know. I would love to have that conversation with Elon Musk, and we can kind of talk about it. He's a busy guy. I understand. He is the one with the rocket company and the cars that run on electricity. So, I think it's important to take what he says very seriously, but I would be really interested to see if that actually happens over the long term, or, colonizing Mars, colonizing the moon is just this temporary thing that we try to do and then realize that in fact Earth is the best. I do sort of see sort of for the longer term vision, as Jeff Bezos is sort of saying, eventually there'll be trillions of people living in space. And I do see that, like, 200 years from now, when we've got serious infrastructure in space and it's just easy to live in space, and you hop on your space elevator, you get in your reusable rocket and you fly to the hotel that's in orbit, and then you take a transfer shuttle to the big orbiting colony. Like, all that makes sense, but it's that in-between time that I think we're going to make. I sort of think about, like, when the Vikings tried to make it over to Canada, and you've got all of these bones of starved Vikings in Newfoundland because they just couldn't survive. So anyway, that's my thought. I don't think that definitely most millionaires and billionaires aren't going to want to leave Earth. So if you've got people like saying that as like some kind of conspiracy theory, that's nonsense. Except for Elon Musk. And like Jeff Bezos doesn't want to leave Earth. And I think Musk is the one. And my guess is he will change his mind. So, we'll see what happens, right? Put me down for Musk changing his mind. Raza Siddiqui says, can Elon Musk make electric-powered rockets? Well, he kind of does, right? SpaceX is sort of an electric-powered, when the Starship flies, it's going to fly with methane fuel. And the methane is going to be made by using a method that allows you to essentially pull carbon dioxide right out of the atmosphere and mix it with water to be able to produce methane as a fuel. So you're going to have solar panels that are pulling in, that are producing the electricity that will drive this process. So any methane fueled rocket that is built using this process will be electric powered, will be solar powered. It's just, you got to go through one step before you actually turn it into solar power. And in theory, they'll be carbon neutral. Although we don't know what the difference is between firing your methane, when you fire your methane rocket down in the low atmosphere, you fire it up in the higher atmosphere. Are you moving carbon dioxide around into different layers of the atmosphere that you don't want The other thing that's really interesting, and we were going to report on this for Universe Today, but I think we sort of have stalled out on it. But some people are developing a solid rocket motor that you can actually turn off and on with electricity, kind of like the way you can turn a regular liquid rocket on and off. Because the problem with solid rockets is they just, once you turn them on, there's no turning them off again. And of course, we've seen with disastrous results what can happen with a solid rocket motor. So it'd be pretty amazing for safety purposes to be able to turn those off and on. All right. Larry Beckham, doesn't Starlink have electric thrusters? Yeah, I mean, an ion engine is an electric thruster, but you are still using a propellant. So you've got xenon, or in the case of the Starlink satellites, they're using krypton, and then you are accelerating, using the power of the sun to accelerate these little particles off of your spacecraft and out into space, and that's giving you a thrust. So yeah, that's electric powered. Although to be even cooler, I love the idea of an air-breathing ion engine, because then you're pulling in your propellant right from the atmosphere. You don't actually need to carry any propellant on board. You just suck up particles of the Earth's atmosphere, and then you throw them back out again at high velocity using your ion engine, and then it never needs to be refueled. It only works in low Earth orbit, of course, but it's such a great idea. Let's see. Someone asked, apologize, can't read the name. What would happen if Mars collided with Jupiter? Let's suppose that Mars drifted from its normal orbit to Jupiter. Would it affect the inner planet system, Mercury, then Earth in any way? Thanks. So the important thing to remember, of course, is that if you remove planets from the solar system, you make things more stable. So if you removed Mars, if you removed Jupiter, if you removed Uranus, Neptune, you would make all the other planets a lot happier because they would have less gravitational interactions. And there's no real force that's going to push Mars out into Jupiter. Kind of. The sun is losing a tiny little bit of its mass every year compared to its total mass. And that decrease in mass, as it's converting hydrogen into helium and it's releasing energy, some of that mass is being turned into, is escaping the sun because it's turning into energy and it's escaping the sun. And that's decreasing the mass of the sun. And that is allowing all of the objects in the solar system to drift out in their orbit. But they're all going to do that fairly equivalently. So you're not going to get this situation where Mars is going to be pushed out more than Jupiter will and it'll crash in. If Mars did crash into Jupiter, it would be an explosion. We would definitely see it for a few weeks, maybe a few months, and then it would be gone. And it would just sink into Jupiter and come back a couple of years later, and we would never have known there was a planet Mars. All right. Dermot asks, why are LISA and LIGO only two-dimensional or single-planar? LISA could be a triangular pyramid and give us that much more information as we would quadrupedal our planar data. Wow. Yeah. So if you look at the LIGO observatories, you're looking at they look like two L's. One is in Washington State. The other one is in Louisiana. And what they do is they measure as these gravitational waves pass over one observatory and then they pass over the other observatory. That difference, they're able to detect that, yes, indeed, it was a gravitational wave. Use two because if there's a truck driving past your one observatory and you don't detect the same thing, right, then it was a false positive. But in fact, now with the Virgo observatory reaching pretty much parity with the two LIGO observatories, you now have three telescopes that are on, you got the two in the United States and the Virgo observatory is in Europe. So you now actually do have a triangle that allows you to sense where these gravitational waves are coming from. And India is building a gravitational wave observatory, and Japan is building a gravitational wave observatory. And so each one of these is going to give you a better understanding of where your waves are coming from. Up until this point, with only LIGO, they only knew what hemisphere the gravitational waves were coming from. Now they know sort of fairly accurately where they're coming from. With LISA, you've got this, these 3 telescopes arranged in a triangle. And again, that tells you fairly accurately where they're coming from. The next advancement to LISA is this idea called the Big Bang Observatory. And this is sort of planned as the next step after LISA. And this is going to be a, probably 12, I think, LISAs in a gigantic dodecahedron, anyway, 12-sided die, for those of you who play role-playing games. And so it will be able to detect gravitational waves with even more precision, even the gravitational waves that are left over from the Big Bang, which is, of course, this time that we can't see, older than the cosmic microwave background radiation. So it's a kind of amazing technology. And actually, tomorrow's episode, where we talk about L4 and L5 in the Lagrange points, talks about this idea of building a gravitational wave observatory using 3 of the Lagrange points. So for those of you who are patrons, you've already seen it. For the rest, you'll see it tomorrow. Morgan Fumick. Hey, Fraser, would we be able to survive without a pressure suit in any of the underground oceans on the moons? Yes. We actually did an episode which was, where can you survive in the solar system without a spacesuit? And there are a couple of places, right? Titan, you don't need a spacesuit because the atmospheric pressure is like, double Earth's pressure. So you just need to have a really thick coat. And of course, I'm dramatically underselling how thick of a coat you're going to require. But the other place that you could go without a spacesuit is you could swim in water that's liquid, because you're going to have the water pushing against you. Now, you can't breathe, but there will be a time, there'll be a moment where you could go down there and you could go for a little swim, because the pressure and the temperature and all that is going to be roughly equivalent, which is kind of amazing. But then you would die. So don't do it. Sorry, apologize to the podcasters who are listening to me. I'm looking at the comments. All right, Hernan Jose Santos says, how is the Planet 9 search going? No luck so far. I know that Mike Brown and Konstantin Batygin have been searching for Planet 9. Other astronomers have been doing this as well. Everyone is really waiting for the Large Synoptic Survey Telescope, which is going to be built in 2021. So we're about 2 years away. And this instrument should be the one that actually turns up Planet 9, mountains of Kuiper Belt objects, other asteroids. It's going to turn up all kinds of supernovae, all kinds of super weird things that are happening out there in space. So wait another couple of years. It's probably the mission, the telescope, if anyone's been watching my channel, I am the most excited about it. Brandon Warren, why hasn't Tim Dodd finished his Aerospike video yet? Oh my God, poor Tim. You're asking me why? Tim Dodd gets so much grief for the amount of time that he takes to create his videos, because they are awesome. Did you watch his raptor video? I mean, he went and stood beside a raptor. And so his Aerospike, I know he's gone and actually is trying to shoot the Aerospike engine. So give the man a break. He's trying as hard as he can to make videos. I just stand in a damp Vancouver Island forest and talk about space. That man goes to Boca Chica and videos rockets launching. So, yeah, poor Tim. He's working as hard as he can. Yamagashi's son. Interesting. Does gravity move at a different speed in an atmosphere than it does in a vacuum? I don't think so. That's a question that I don't know the answer to. That's interesting. So gravity, we know that gravity moves at the speed of light through a vacuum. But does gravity move at a different speed through something, like through the Earth? Some physicist or scientist is going to have to answer that one for me. I've never thought about that question. Like, okay, who was it here? Yamagashi-san, could you do me a favor and could you email me that question so that I can find an expert to answer it? Just email frasercain@gmail.com, or post it as a comment on a video like my latest question show, and I'll try and catch it, because I will try and find somebody who's an expert in gravitational wave astronomy to look into that one, because I think that's a great, I mean, it is a question for Dr. Paul, but you know, I mean, like, let's go talk to an actual gravitational wave astronomer. It's such a great question, because we know that light can move a different speed, right? Light can go, is a different speed going through water, is a different speed going through the atmosphere, and is a different speed going through rubidium crystals. But does gravity move at different speeds through different things? Yeah, I don't know. That's a great question. All right. Romulusek, do you expect any difficulties during crewed missions to the moon and Mars? Yeah, so many complications, so many difficulties. This is why I think if we are going to do a crewed mission to, say, the moon, you want to, or to Mars, you want to start with the moon, because you want to work out all of the bugs. And there will be a lot of bugs, right? You ideally want to have a crew of astronauts spend the amount of time that they would spend flying to Mars, but you'd want them to do that flying to the moon. So maybe go on some orbit where they're in a big long orbit. They've got all the exact same materials that they're going to require for their landing on Mars, but they are just orbiting around the Earth, around and around and around for 9 months. And then just figure out every single thing that goes wrong, right? Oh, their toilet doesn't work properly. Oh, they ran out of food. Oh, they got space madness and tried to kill each other, right? Then you can deal with all of these situations, because all you have to do is have them deorbit and return back to Earth. Once they're on their way to Mars, you have no way to fix it. I mean, we saw The Martian, and we saw how hard it was to try and save a person who's out there on the surface of Mars. So I think that the moon, we saw it's a 3-day trip, right? You fly out to the moon. It's relatively quick. We're going to see the modern technology versions of this, but I think that we are, it's just going to take so much more testing to figure out every single thing that's going to go wrong. And that's why, like, when anyone has said, oh, we're going to go to Mars by 2024 or 2028 or some relatively quick time frame, right? In my mind, it's like I could sit down and brainstorm, and I'm sure a bunch of other people, we could brainstorm 1,000 things that need to be thought about that have nothing to do with the rocket, right? That are like about, oh man, like just like that you would need to adapt. And that's why, actually, say the International Space Station, you know, we've seen Scott Kelly's was on the station for a year, which is about the length of time that you would take to go to Mars. And they got to watch all the things that went wrong. So it's going to be that, but more. And with no chance of saving them. So, yeah. All right, apologies, looking. Hallucination 08. Kyrgyzstan has a video on the Great Filter. If you have seen this, what is your opinion? I've done a bunch of videos. I've talked about the Great Filter, Fermi Paradox quite a bit. I find the Great Filter to be a terrifying thought, and the sort of plausible answer. But I much prefer that we're alone than we're doomed. So I'm just going to stick my fingers in my ear and say, la, 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 I'm not listening. And hopefully we'll go from there. Ben Kalo, yeah, it's a live show. We're back, man. All right. Jay Brookman, if we can't see the entirety of the expanding universe, how do we know how old the universe really is? Great question. So we can, the key came from the cosmic microwave background radiation. And astronomers detected this back in like the 1960s. And this is the afterglow of the Big Bang that's in all directions. And so you look in any direction and you see this. Now, astronomers did the math, and they know that when that light was released into the universe, its temperature was about 2,500 Kelvin. So it's kind of red light, right? Imagine you're looking at a big red dwarf, you're looking at a red dwarf star, a red giant star, and it's like this dull red color. That is the color that the universe was the moment the light was able to escape into the universe. It was sort of, everything was red. And so then you know that space is expanding. And so you look at the wavelength today, and the wavelength today is into the microwave. And so then all you have to do is it's the math. You go, okay, great. So we know the expansion rate of the universe, which is a thing that people are able to measure by essentially using the Doppler method to be able to see how fast galaxies are moving away from us. And they were able to figure out what that speed is. And then you just run the math backwards. And that gets you to a point about 13.8 billion years ago when that light that is now microwave was on the red side of the spectrum. So things have gotten a little more complicated in the last little while because essentially there's two methods to measure the expansion rate of the universe, and they disagree, and they're both very accurate. So so we're still, the jury's still out on exactly what that number is right now, but it is roughly 14 billion years. Janelle Duncan, how would you avoid space madness? Space madness is, I think, one of the least of the problems of space exploration. I think human beings have demonstrated that they can be in enclosed spaces, in dangerous situations, relying on each other, and they're able to get through. You look at, say, what happens with people on a submarine, people in research stations. I mean, yeah, sometimes they go a little crazy and they get really mad at each other. But in general, when astronauts are chosen, they're looking very carefully at their personality types and looking for people who can really get along, who are cool under pressure, right? So there's no surprise that Scott Kelly is a test pilot, right? Perfectly comfortable getting into an F-15 and making it do things that it was never meant to do. So then you take a person like that and you have him float around in the space station for a year. That's no big deal for him. And every astronaut that I've met is they're just delightful people. Talk to Don Pettit, who is one of NASA's hardest working astronauts, and you just get it. Right? You're like, okay, I understand why he is an astronaut. He is super smart. He's up to speed on everything. He's well educated in everything you can look for. He's super interesting. You just want to spend time. Like, look at Chris Hadfield, right? Like, who wouldn't want to just hang out with Chris Hadfield and float around on the International Space Station and let him play the guitar? So I think that of all the terrible risks that we face, space madness, where the astronauts are just trying to really kill each other, is fairly low. Whoa. Samuel Baker, does quantum entanglement ruin the speed of causality? No. It's so funny. Clearly I need to do like one video and then I can just direct everybody at it. So I will do that. Why you can't use quantum entanglement to communicate faster than the speed of light, right? And here's the analogy that I always use, which is like, take two boxes, right? And you put one, I don't know, let's say you flip a coin. Is that right? Okay, you flip a coin. No, that's not right. All right, you have a black ball and you have a white ball, okay? You put the black ball into one box, you put the white ball into the other box. You mix them up so people don't know which ball they have, and then you have them walk away in other directions. And so now you've got a box with a ball inside the box, and the other person's got a box with a ball inside of the box, okay? All right? You can't see each other. You don't communicate in any way, shape, or form. You open up your box, and you see what color of a ball you have. Now you know immediately, instantly, what color ball the other person has. But there's no way to communicate about it. They're not informed. And this is the key. They're not informed that you opened your box. So they don't know if you opened your box. And they don't know if you know the color of the ball. You have to wait. And then you have to call each other on the phone and say, did you open the box yet? And they go like, yeah, I opened the box. I got the black ball. I got the white ball. Yeah. Because that's how it had to work. So the only difference between that scenario and quantum entanglement is that the state of the ball is unknown until it's observed. And when it is, the other box responds accordingly. But there's still no information being communicated back and forth. And that's the problem. So you can never use quantum entanglement to allow you to communicate faster than the speed of light. You can't use it to probe the inside of a black hole. The only thing that you can use it for that's been thought of so far is to essentially prevent people from eavesdropping on your communications. So in other words, if you can essentially detect if someone has actually collapsed the wave function, then you'll know that your communications have been intercepted. But apart from that, we don't know. So I'm sorry, that's a Canadian sorry, that you can't use quantum entanglement to travel faster than the speed of light, even though the entanglement could happen billions of light years away instantaneously. You still can't use it. All right. Martin's T. What year will we prove black matter exists? I'm assuming you're talking about dark matter. Define exists, right? That the observations for that dark matter is there, that it is a real thing, have been there for 50 years. And the observations are getting better and better and better that this thing exists. That they can map out the concentrations of it. They watch as it distorts the light from more distant galaxies, as these blobs of dark matter are moving in front. They know it's there, but they don't know what it is. So the question is, like, what do you know? Like, when will we know what it is? And we don't know when we'll know what it is. We may never know. The various people like astronomers, physicists have sat down and said, okay, what could it be, right? What could it be? What's every possible thing? And like, it could be that gravity works at large distances in ways we don't understand. It could be that it's a particle that we've never seen that doesn't interact in these funny ways. It could be black holes. It could be all kinds of things. And they go, okay, great. If it's black holes, what would we expect to see? And then they go and they run all of their various observations. They would expect to see all these things. And in the end, they don't see those things. And they said, well, if it is gravity, right, working in ways we don't understand at large distances, what would you expect to see? And then they don't see those things. And so that's why they're leaning towards the particle idea, because it's still kind of, if it was a particle, it would behave in the ways that astronomers are seeing. But what kind of particle? What produces the particle? Where are the particles? Why can't we find them? Right? That's science. And again, it doesn't drive me crazy exactly. It gives me mild amusement to watch people who think that dark matter is some kind of sham or some kind of fraud that's being perpetrated by the being done by the scientific community and perpetuated by the scientific community, perpetrated. Anyway, by the scientific community because reasons, because, they need to make something up. But this is just how science works, that we're halfway between understanding this thing. And think about the time when people were discovering electricity, right? Like, what is it? If you can't explain what it is, then it doesn't exist. Well, no. Like, there are sparks that you can generate. You can repeat the experiment. You can see lightning. It's a thing. We just don't know what it is yet. So just give it time. right? Just let scientists keep working on it and they will get a better sense. And they're going to have to throw out 99.9% of their theories until they get the one that is the right one. So, and that's how the process works. And it just happens to be that you're living at a time when this is one of the mysteries. And back in history, there were other mysteries that people got to live through and experience in real time. And I find it exciting to hear every new idea and to hear what the evidence, to hear what the data say, and to see them get thrown out or see them get established. It's like, I don't know, it's like watching a sports ball game for people who like to watch sports ball. All right. Venkatesh Mahadevan says, Fraser, is it possible that dark matter is actually antimatter? It's not possible because we would know what antimatter, when it interacts with regular matter, annihilates and releases a tremendous amount of radiation. And so in form of gamma rays. And so we would look out into space and we would see gamma rays. So you can imagine, right? This is the conversation a bunch of astronomers had. They're like, could dark matter be antimatter? And then someone said, well, if it was antimatter, then we would see gamma radiation in all directions from antimatter, 10 times the antimatter, colliding with regular matter. Do we see that? No. Okay, antimatter's out. Next idea. That's how it would work. Oh, Donovan Gustafson. When are we going to visit Neptune again? 20 years out. I don't know. We really need to go back. We need to go back to Uranus and we need to go back to Neptune. And I understand Uranus. I get to say, we're going to send a probe to Uranus to study its gas. That's fun. But yeah, we really need to go back to these worlds. Let's see. Man, my voice is not used to this. So FPTCP says, Fraser, doesn't the Fermi Paradox make you feel less afraid of AI and the possible technological singularity? I mean, where are all the AI aliens? Yes, exactly. So this idea, right, of the existential threats that face humanity, one of them is, of course, the robot uprising. But robots can go to space, right? Robots can fly spaceships and chase us down. So the fact that we don't see robots colonizing every nook and cranny of the universe makes me feel pretty good that if the Fermi Paradox or the Great Filter is a robot uprising, that's not going to happen. Whew, cross one off. Now we just have the other 99.9 ideas, and especially the ones that we can't think of. Francis Vacon? Fraser, do you know of a serious protocol guidelines drafted in case we find proof of intelligent civilization in contact? If not, by when do you think we may see a government agency initiate it? Yes, we do. Yes, there is. I forget the name of it offhand, but I did a video all about it. So let me find the title. So it's, if you go to my playlist of all the videos, here, I'll just put it in, I could put a link. There you go. I put it into the chat. The title is, What If We Do Find Aliens? How Prepared is Earth for Meeting Extraterrestrials? And the gist is what you just said, that in fact, scientists have come together. They have written up rules. They've got a way of measuring the amount of risk. And they've already got some ideas on how to deal with it. So, yeah. Let's see. Eric 1. Are there plans to send an asteroid hunter to the L3 Lagrange point? The sun wouldn't be blinding us there. No, there are no plans to send. So, I've done an episode on the Lagrange points. Part 3 is coming out tomorrow at noon, precisely, I promise. And so we talk about with the L2 point that was one idea for a place to put a telescope that you could hunt for asteroids that maybe we wouldn't see. And you don't need to go all the way around to the other side of the sun. And the problem then is you can't communicate back to Earth. You just need to be at a place where you're not getting as much glare from the sun in the same place, right? So you just need to be able to see off to the left and the right of the sun, and you should be okay. You'll get most of them. Mobius X, what's the deal with Saturn's rotation? I don't know. I think we're going to be covering this. And just this idea that in fact Saturn is actually a very difficult planet to pin down the speed of its rotation, and it looks like the way that they've done it is they used data from Cassini to try and map the way its magnetic field is turning. But it looks like, in fact, the magnetic field changes enough that it makes it really hard to tell how long the day takes on Saturn. So maybe I'll do a video on that. I don't know. It's an interesting idea, right? That in fact, there's no way to know how fast a planet is rotating precisely, which is such a weird idea. I got about 9 minutes left. Sean Marson, Fraser, can you talk about why we're hearing about more near-Earth objects lately? Is it there are more of them, or we're looking for more? I think that this is just a confirmation bias, that you're noticing more articles about near-Earth objects now than you were in the past, but those articles have always been there. I mean, literally, as long as we've been reporting on stuff, we've been talking about near-Earth objects. And I remember kind of getting this wake-up call. It must have been like 15 years ago, when pretty early on in doing Universe Today and writing about this kind of thing. And I was writing about how there was going to be this near-Earth flyby of an asteroid and how cool it would be, and how there would be a chance to be able to see it in your telescope. And then I was running across, and I was getting a ton of traffic to this article, and I couldn't figure out why, because it was a fairly bland, you can see an asteroid as it comes by. And it turns out there's a bunch of places that were writing these big scare stories about this asteroid. And so I had to come back around and write a no asteroid, 2005 is not going to hit the Earth. And then I had to write another one, and then another one, then another one, right? And just this idea that these asteroids come close-ish to the Earth, and then that's compounded by people who are looking to do clickbait, right? They're looking to get traffic to their article because they want to scare you, because, yeah, there's an asteroid. Yeah, it's coming close, but they do that all the time. So don't worry about it. It's been happening for billions of years, and it's going to happen for billions of years into the future. And the chance of any one large asteroid crashing into the Earth is incredibly low. So, on the internet, anybody can say anything they want, right? And it could be fake news. So my hope, right, and I actually dealt with this in the last question show, right? Like, what are my credentials? Why am I allowed to talk about space news? Who gave me the right? And, and that's where I think it's important to show up on a regular basis, to try to not be too clickbaity, to get enthusiastic about the discoveries, but not try to do the fear mongering, and be a trusted source for space news. So I don't really, we're sick of asteroids are going to come close to the Earth stories. Unless it's something really interesting, we just avoid them, because they're, there was an interesting one where, and like when anything gets put onto the Torino scale, that's pretty fascinating, because then astronomers have actually given it some risk factor into the future, and we'll usually report on that. And there was a really interesting story where an asteroid got put on the Torino scale. It was a fairly large number on the Torino scale, and then it and then it was removed again. And it's just that this happens all the time. And that process is pretty fascinating, how asteroids, they make a threat assessment on the asteroid and then they realize that there's no problem and then they remove it again. That's very interesting. But just the fact that an asteroid is going to, and if it's really close, or if there's a way that we can see it, or if it's got some use, or if it's got some familiarity, then we'll cover it. But you'll actually find we don't really talk about them much. It's not interesting to me. And at the end of the day, isn't that what this is all about? You're just following my curiosity. Mike McHugh, do they do autopsies on astronauts that have done long duration missions? I would assume they have. I don't know if there's any specific autopsies, but I mean, they've been tracking the cardiovascular health of the astronauts. I mean, those astronauts, like, you go to space once and the doctors want to, take blood samples from you for the rest of your life. And that's just one of the prices that they all have to pay. And so they're trying to track what are the downsides, what are the health implications of all of the missions that they've done. And when you think about, say, the Apollo astronauts, I mean, they were only in space for a week. Well, you've got people like Scott Kelly up there for a year. A lot of Russian astronauts have been there for very long periods of time, and they're still trying to get a sense of what the implications are. So I think I would assume they get autopsies. I haven't heard like an official report though, so, but I'm sure NASA doctors want to know what happened and if spaceflight had any impact on their bodies, and especially some of the parts that they can't check until afterwards. All right, we're about 3 minutes away. A couple of things that I wanted to just talk about before we get back at it. One is the weekly Space Hangout returns in 2 days, on Wednesday at 5 p.m. So at the same time, but in 2 days from now, and that'll be the weekly Space Hangout. That's going to be over on the weekly Space Hangout channel. I'm sure someone in the chat will post a link over to there. But, if you enjoy that roundup of space news with me and a bunch of other space journalists, then you should definitely join us there. Our special guest is Dr. Alan Stern, of course, the principal investigator of NASA's New Horizons mission. So if you want to definitely not ask him about whether Pluto is a planet or not, come join us and talk to Alan Stern. And we're going to be bringing in some new science communicators, which is going to be a lot of fun. The goal this season is for us to try and train as many people who want to sort of become a better science communicator. So I think it's going to be a lot of fun. There's a lot of fresh faces, and I'm really excited about these people joining us. And then, of course, we've got Astronomy Cast is back in season as well. The one we did on Friday was all about reusable rockets. I have no idea what this Friday's episode is going to be about. But you should check it out. And tomorrow is the third episode of the Lagrange series, all about L4 and L5 and some ideas that you probably haven't heard of. And then I don't know what we're going to do for the next episode. We were all planning to do one on the Indian lander, and I was so excited to talk about the history of the Chandrayaan missions and now that the lander's safely on the surface, but of course it failed, and so I don't want to talk about that. I kind of want to talk about landing failures and just how hard it is to land, and so all the people who were so hopeful about the Indian landing to not feel so bad. Thanks, Sebast1509. I appreciate that. So that's an idea. I haven't really thought about what I'm going to do, but my previous plan is in the garbage. So that's why we waited to the last minute to do this episode. Anyway, and then the last thing is later on Wednesday, I'm going to be doing an interview with John Michael Gaudier for his channel. So that'll show up in the feed, and I will include the audio of that on my podcast feed as well. So if you haven't already received that, definitely check that out. All right. Hey, thanks everyone for joining me back on Open Space. I really appreciate it. Super fun. Again, I really enjoy this. I apologize that I can't get to all those awesome questions. I'm looking at like more than 100. A huge thank you to all of the moderators and the people from the Weekly Space Hangout crew who were copying the questions over so that I could take a look at them up there. It makes my life so much easier, and I know it's hard, but I really appreciate it. It allows me to see as many of those questions as possible. So a big thank you to all of them. All right, well, let's wrap it up. I will let you know. I'll post a schedule for the upcoming episodes and hopefully some of the new guests that we're going to have on the show. So stay tuned. All right, we will see you all Wednesday or next week here on my channel. Thanks, everyone.